Section 3.1, it's been fun. 5.1, huh? We're in BC. We're at chapter 5, although our book is tiny and it just flies. So, extrema. You guys know what's going on. The highs, the lows. Never mind. What do you guys think is coming?
Sign chart.
Yeah, probably. What else?
How high is your Y?
How high is your Y?
Yeah.
Ooh. So like maximum value?
Yeah.
The max versus a max? What's the difference between the absolute and a? Relative. Good. What's the difference between how we solve for relative versus absolute?
Relative, you check the endpoints of the Y values, and then absolute, you plug in. I don't know.
No, relative is you do how high is your Y.
I meant absolute.
Is that wrong? Am I right?
You guys are both saying the same thing and it's switched. Relative. Sign charts. You're trying to look for regions where there's a high, where there's a low, and you look at DNEs and horizontal tangents, aka?
C value.
Yeah, critical numbers. Good. Critical numbers, critical values, look for changes in sign. They're saying, how high is your Y? They're saying, check the endpoints in the critical numbers. They're saying, table absolute, right? If a function's being cut off, absolute. What if they ask for the extrema on an open interval?
You do sign chart. I'm kidding.
Test the endpoints as well and sign chart, put it all together and say, ooh, is there a absolute max? Is there an absolute min? Maybe it's decreasing forever, so there is none. You have to consider both if they're asking for absolute. So always absolute considering endpoints. Just consider, if it says open interval, you have to consider the behavior as well. Okay, ooh, that was totally my dad thing to do. That's weird. Anyway, extreme value theorem, EVT. What's going on? It's a forever card, by the way, my forever people. EVT, extreme values, maximums and minimums. Absolute maximums and minimums are guaranteed if the function is continuous on a closed interval. Good. Continuous on a closed interval, there will be a max and there will be a min. There will be an absolute max and there will be an absolute min. Relative. Could be at sharp points, could be at horizontal tangent lines, will never be at vertical tangent lines. But could be at DNEs and could be at mean sharp points, and it could be at horizontal, so you have to check them all. I don't think really we need to draw graphs unless you want to, right? But just a reminder, it could be at either horizontal tangents or sharp points, aka where the derivative is 0 or DNE. So, quick reminder. Is it quick? Yeah, it's really quick. How many pages of notes was this last year? I don't know, days. Days of notes. Forevers. What? All right. What's going on? Let me zoom in. So we take it piece by piece. When you're finding relative extrema, first of all, think about the domain. If they don't give you an interval, you have to think about the natural domain if there's something implied. If you have even roots, if you have ln's, if you have tangents, exclude the discontinuities in your analysis, but include them in your sign charts. Exclude them as candidates. Vertical asymptotes cannot be maximums or minimums. Neither can holes. Neither can holes? Discontinuities cannot be maximums or minimums, but they do need to be included in the sign chart. Where are we at? What's wrong? Check denominator? Nth root of u, where n is even. So even roots. I'm doing my domain problems. So even roots, logs, and trig. Does that make sense? Square root, fourth root, sixth root, eighth root, yeah. Yeah. Oh, symmetry. No. I didn't put down fractions, but I figured that was just assumed, right? Find critical numbers, aka take a derivative. As a fraction, do so. Horizontal tangent lines come from the numerator equaling 0. Vertical tangent lines come from the denominator equaling 0. Beware the ones that make it 0 over 0. Our book calls horizontal tangents stationary points. Did that come up last year? Stationary? I don't think so. So when you see stationary points, what is it talking about? No. If something is stationary. Come on, you guys have heard this, haven't you? A stationary bike, like in a gym? What's a stationary bike? Doesn't move. Oh, doesn't move. The velocity is, oh, it's a horizontal tangent line. Stationary points. Does that make sense? At that point, the motion is stationary. Does that make sense? Yeah. Because it's the x equals for the horizontal tangent line. Huh? I didn't hear the initial comment, but I heard the same, not same part. Doesn't really help. Okay, number 3. It's okay, it's okay. I'm just going past domain. Is that okay? Sign chart. Sign chart. It's 4. Thanks. Guesstimating? Riemann sums. That's integration. We're not there yet. Area under the
That was like our last lesson.
curve. No, that was disc and washers.
Oh, yeah.
Yeah, about there. January.
Like when do you have to like turn a graph into like a 3D object?
Well, wait a minute. Was turning the graph into a 3D object, was that the objective, or was the volumes of the object that we modeled with a graph the point?
So like
No. I was just, because, I mean, taking a graph and making a 3D, I mean, there's 3D printers. We could talk about that. But that's not a good application of what you're saying. Well, it kind of is, because based on rotation. But being able to deal with irregular objects, their volume, their densities, that's where it would be applied.
okay, so just like for shapes that aren't like basic
Right.
squares or circles or like
Right.
finding those volumes.
Which could be anything from like a jet engine, right? And or like the hull of an aircraft that needs to fit the engine, etc. There's a lot of shapes that aren't just perfect cylinders or rectangular prisms or pyramids or.
But how would they like before they did like the disc or the washer? Like how would they plot those points? Like
Well, you'd have to think of the dimensions and probably get it into like a program. Then you'd be able to make a model, like from a model of it, you'd be able to define the parameters, and from the parameters make a function, and then be able to. Which all that would probably be in computer programming. Like it wouldn't necessarily be you reinventing the wheel every time, but.
wait, what?
You never heard that before?
Yeah, I have.
Oh.
But I just
Reinventing the wheel is like going back to the very beginning and like doing it all yourself, as opposed to using some sort of program. Yeah.
caught my attention because like NASA, like for one of their like Mars rovers, they like reinvented the wheel because like they needed to create a wheel that would like survive the terrain of Mars. So like they use like this like alloy. I don't really know what's in it, but like it allows like the metal to bend completely, like all the way to like the frame, and it'll go back like to its original shape without like any permanent damage.
Oh my goodness.
So yeah, it's really
That's really cool.
yeah, they reinvented the wheel.
Quite literally. That's cool.
It's really interesting.
Yeah, it is really interesting. Huh.
It was like, it actually is rocket science.
Oh yeah. No, someone found the rocket science thing online when they were Googling. And then Jason Johnson loved everything like NASA, and then we just kind of went with it. He would come in and doodle, and then yeah. But we basically sent a design, and then it was just, yeah.
So we're gonna do SpaceX.
You guys ponder it. Play with it this weekend or something. There are tons of applications to calculus. You can think about how it's applied. It doesn't necessarily, I think it was Hidden Figures. We watched Hidden Figures 2 years ago.
That's such a good movie.
Yeah.
That's right. It had just come out, and we watched it for the end of the AB exam, not last year, but the year before. Last year, like, everyone had seen it, and then time was so short. Like, we barely had any time last year after the AP. Yeah. We only had, like, 3 days, 3 school days after all APs were done. Calculus had a little longer, but the year before, we had, like, 2 weeks or something. Your sophomore year. I feel like there was a lot of time in between. Because last year APs were the second week of May. The year before it was the first week. So we had more time to watch stuff 2 years ago. So the APs was the second and third, we got the fourth. We have our first derivative sign chart with increasing and decreasing. You guys can see your critical numbers. I put in critical numbers and discontinuities. Remember, these guys are allowed to be relative extrema. He's not allowed to be, even if there's a sign change. We just got to keep an eye on the domain. Check domain. That's what I kept on saying last year. Down here, second derivative test, we know about concavity as far as the graph behavior, at least. How do you use the second derivative test? How do you use the second derivative to check for relative extrema?
Second derivative?
Yeah.
If it's positive.
Careful. Don't use it.
Boy,
By checking the concavity of the second derivative.
No, don't say that. Don't say that. Mm-mm. Concavity of the second derivative is looking at the fourth derivative. Don't do that.
Concavity of the first by looking at the sine of the second derivative.
First derivative? That would be the third derivative. I know, but the AP graders won't, and they'll be like, ha, 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 ha. Okay.
So if it's positive, that means it's concave up.
What's positive?
The graph at C.
Okay, wait. I think
F double prime is what you want to say. So if F double prime is positive, then
Then it's concave up. The function is concave up, which means that there's a relative min at C.
at C. So when you're dealing with critical numbers, right? Just because a function is concave up does not mean, think e to the x, does not mean there's a min, right? You have to have concave up at a horizontal tangent. True? What if the concavity is 0? Oh, it's not a min or a max. It fails, and you have to go back to the first derivative test, because what about absolute value? Absolute value has no concavity, but does it have a min? Yes. So the second derivative test only works when there's concavity. When there's not concavity, well, we can't do it. But what's the difference? First derivative test, you need to know before and after a critical point. True? So only if the AP gives you something where you can check before and after can you do the first derivative test. Second derivative test, all you need to know is at the point. So all you need to worry about is at C. What's the concavity? You just get to plug in and only deal with C. So you guys hopefully remember that the AP doesn't always allow you to know before and after. Sometimes you only know the at, and you have to be using the second derivative test. That's a lot of stuff we just packed into one page. On a fire drill day, nonetheless. All right, we got it? Anybody want a picture before I change the slide? So, let's say you're given the following function f. Let's say you're given the following function f. We're trying to describe f prime, and describe f double prime. Is our shepherd. So, coming back. F, wouldn't we think of y values? Let me zoom in, because some of you are overwhelmed. You're welcome. I made this up 2 years ago. It was Georgie's class. 3 years ago? Where are we looking? Oh, because I went A, B, C, D, E, F, and then I wanted a G. Because C wasn't exactly halfway, so then I made G the point of inflection. Does that make sense? Sorry, I did A, B, C, D, E, F, and I'm like, wait, C isn't the point of inflection. Okay, fine, there's a G. So much judgment, because it was after F. If I started to erase that, then I erase it all.
See the judgment in real life.
I know. See, then I move my point. Now I have to like disconnect everything. Oh, hope you guys are happy now. I hope you're happy. I hope you're happy now. I hope you're happy now. To feed your ambition. Good song. I've seen it too many times. It's coming back. Isn't it December? To Pantages, Wicked.
Didn't even remember.
Literally, who else?
Who else?
Who else would have been?
Yeah, you're right.
Okay, now are we ready to talk about it? So given a graph of f, f is the y values. Who's f prime? How do I see him? How do I visualize him? This is a regular graph, yeah. Yeah? Guys, when the function is increasing, the derivative is positive, and when the function is decreasing, the derivative is negative. But long story short, aren't we just looking at the slopes? How do we think about f double prime? Concavity. I just gave you a nice simple graph. Maybe I should have done a graph of a derivative, but we're building. So let's talk about all these things I want you to fill in about them. All right, what's the domain of f? I think I should do a different color or else it's going to get confusing.
Negative infinity to
Yeah, so 4f, then 4f prime, then 4f double prime. No, we have so much to fill out. It's okay. Is homework due tomorrow? Let's do the next day. But do you guys see we have our work cut out for us at the beginning of class tomorrow? I'm having us put in one big old page like all the different possible relationships, and then we'll build on it to be ready for homework on Monday. Bye, guys. Worship night. Or whatever else you guys decide and choose to do. Happy Thursday.